So welcome back to the second day. So we're gonna start off the day with Chris here, telling us about exceptional Hirzebruch Riemann Roch Theorems.
Okay, well, thank you for the introduction. So this talk will be about two very prominent rings in enumerative geometry, which has already appeared yesterday during one of them during Federico's talk, another one during our math overflow session that Alan gave us. But let me still remind you. So let's say I have a smooth projective variety, X. There are two rings. The first one, we can call it Kx. And because X is smooth, although Alan made a careful distinction of the cohomological one and the homological K, for smooth things, they coincide. So I will not really distinguish them. So I will really write down what Alan called a cohomological version. So what is this? This is finite rank, vector bundles on X modulo short exact sequences. Or whenever I have a short exact sequence, the outer two things sum to the middle. So that's the K-ring. And then there's the Chow ring, that I'll denote as A of X. And this, at least definition-wise, this is, you look at free abelian group generated by sub-varieties, modulo rational equivalence. Won't really matter exactly what it is. If you would like to, you can sort of think of them as the cohomology ring, the singular cohomology ring, let's say with coefficients in Z. Although, of course, experts would know that there is, in general, no natural surjective or injective map between the two. But for varieties that we'll look at today, like toric varieties, they actually happen to coincide. If you like to just think homology ring, that's also okay. And both of these rings have a distinguished map to the integers. Well, the first one, you take the Sheaf-Euler characteristic. And for homology, you can take the degree map, or if you're thinking topologically, capping with the fundamental class, and so on. Now, in all three of these works, the high-level overview of what goes on is the following. You start with some combinatorial object, let's say a matroid, M. Or if you like more realizable picture, matroids are in some sense combinatorial abstractions of linear subspaces, let's say L. And from this data, you can build some vector bundle on some nice variety. And in general, if my matroid is not actually a genuine linear subspace, one can build a K-class. And I mean, why only stick with just matroids? There's also this object called delta matroid, which is some generalization of matroid in type B setting in a certain sense. Realizable picture is that we're now taking combinatorial abstractions of isotropic linear subspaces. So the game is, okay, I have a combinatorial object that generalizes in a certain sense some data in a linear subspace. Now I'm given a linear subspace, so, well, what do? If we can try to build some interesting vector bundle out of that linear subspace. And you end up with a K-class, or you can also try to do things in the Chow ring by looking at the Tseng classes of these K-classes. And by studying these vector bundles and what happens in the K-ring or in the Chow ring by looking at Tseng classes and doing degree computations or Euler characteristic computations, you hope to get some interesting results about the matroids or delta matroids. And in a high-level overview, that's all three of these papers. Of course, implementation takes work, but that's the goal. Now, for some of you, I'm sorry to tell you this talk will not be about matroids, but it will be about a key technology common to all three of the works, although one has to work to adapt it to each situation. It's a common technology that relates these two pictures, or more precisely, these two rings, in a way that's rather unexpected, or at least I found it somewhat unexpected. So talk will be about relating K and A for very special toric varieties, and that plays a rather critical role in playing this game of trying to understand matroids through either the K class or some Chow element classes. So let me start by explaining the combinatorics of the K-ring and the Chow ring in the context of toric varieties. So let's start. That sigma be a projective unimodular fan. Now, if the terms projective unimodular doesn't mean too much to you, that's okay. All I mean is that you take some nice lattice polytope. Maybe it looks something like this, Q. And you look at its normal fan. We can think of sigma as being something of that form. Take a nice polytope, lattice polytope, and you're looking at its normal fan. In geometric language, what we're saying is, let's consider a projective, smooth, toric variety. If you like toric varieties, you can think completely in that realm. If you don't know much about toric varieties, just the combinatorial picture will be fine too. Now, given a fan like this, we can consider what's called a deformation. Say P. And I'll denote that something is a deformation by writing that it's an element of the deformation. Now, what is a deformation? It's a polytope. Sorry. Let's stick with lattice polytope. So it has vertices being integral vectors. Lattice polytope whose normal fan coarsens the given fan. So if I were to do an example, let's look at this P. Normal fan looks like so. I hope you agree that's a coarsening of the previous fan, hence P is a deformation. If you are thinking toric geometrically, we're thinking about a globally generated line bundle. But that doesn't mean much, no problem. Now, given a deformation, we can make two distinguished functions from the ambient space, Rm, say, to R. Here's the first one. Maybe I'll use a different color. Which I'll denote as bracket P. And what is its value at some point Z in the ambient space? It is as what the term says, indicator function. So 1, if the point is in the polytope, 0 otherwise. Indicator function. Okay. So that's one function one can define as soon as I have in fact, any polytope really, doesn't even have to be a deformation. And the other function, which I'll denote as H sub P, often called a support function for the polytope P. What is this? Well, the value at Z is the minimum among all pairing, let's say, in the points in the polytope Z and point in P. And let's just take the pairing to be the standard inner product. And if I were to do this example, let's give this a coordinates so that we're on the same page. Let's do one example. So let me give coordinates like so. Then if I'm looking at the support function of this, well, on this region, it will pair with this vertex to be minimum, so it's constantly 0. On this region, it pairs with this vertex to be minimum, so this is x. So it just picks out the x coordinate here, y coordinate here, and constant. And something you might notice that this is a piecewise continuous, piecewise linear function on the normal fan. Okay, so
Should we
yeah.
think of these functions as defined on the same space or on dual space?
So the fan will live in a certain space. The function is defined on that space where the fan lives. So it's from the space that fan lives in to R. In other words, you can think of this element, at least piecewise, is given by elements in the dual.
And the other one?
And the deformation lives in a space that's dual to the ambient ring space that fan lives in. So, any other questions?
So P is bracket P is a function on the space of the polytope, and HP is a function on the space of the fan. Is that?
Yes. So they technically live in different, over different dual lattices. Yeah. But yeah, normally I might try to really distinguish the two lattices. I'll just have RM with inner product for today. Okay, so given these two functions, there are, well, we can build two rings suggestively named K of sigma and A of sigma. So what's K of sigma? You take the subgroup of functions with values in, let's say, integers, given by indicator functions of deformation. Modulo the relation that if I translate my polytope or deformation by an integral vector, it's the same. And the ring structure on this is a priori not too clear. How do I multiply three things? Minkowski sum. So the sum here really is pointwise sum. For instance, if I were to add this polytope, a line segment vertically with the horizontal, it will give you this. So that's the K-ring, at least so far it's just defined for a unimodular projective fan. Let's do the so-called A ring, or what we'll call Chow ring eventually. So this is built out of the support functions over all deformations. Turns out in our assumption, under our assumption that we're working with projective unimodular fans, you can also actually think of this as piecewise polynomials. So the claim is that these piecewise linear functions arising from support function of deformations actually generate all piecewise polynomials, where the requirement is that, well, you have polynomials on each of these such that they agree on wherever the two constants. A priori, this is not too clear, but you can trust me. And then modulo the relation of taking out modulo the ideal generated by global linear functions. inside the ring of piecewise polynomial.
So these are splines.
So in Ferrigo's talk yesterday, he exactly remarked these are splines. Thank you.
Wait, and to clarify, in the equals on the top, you don't mod out by anything? Or they're both
Sorry.
modded out by?
Let me do
Okay.
this. Thank you. Okay. And there are two distinguished maps to Z, as one might expect. And with this description of these two rings, this Euler characteristic map and the degree map have the following description. So it's determined by assigning to each indicator function of a polytope. Well, on the K side, it counts the number of lattice points. Whereas on the Chow side, if I take a support function of a deformation, take it to the top power, it returns for me the volume. Where the volume here is normalized such that standard lattice simplex gets volume 1. Okay. And I saw this coming all along. So this is from yesterday. This ring as defined is the Chow ring of the associated toric variety. And it's actually not too clear exactly who to attribute it to. But I think Danilov, well, it's not a joint paper, but these two references, I think, will be a fair reference. On the K side as well, it's as expected. Now this identification, I'll say it was implicit in many works, for instance, in Fulton Sternfeld's. It's implicit there, although it's over rational coefficients. It's implicit in works of McMullen. It's also implicit, although there real coefficients are used, it's sort of in the work of Morelli, which actually has a slightly different notion for dealing with this notion of valuativity and so forth. So as exactly stated here, it appears in the appendix of my paper with Junie and Matt. But the ideas were there for quite some time, and we wrote down that this really is the A description for the K-ring of the toric variety, for smooth projective toric variety, even over the integral coefficients. That's one place, but it's been sort of in the literature for quite some time. Okay, any questions so far? So that's the combinatorial description in the toric variety case of these two rather prominent rings.
Is there a counterpart of this result known for algebraic Bordism?
I don't know.
Is there an equivariant version?
So in both cases, if I didn't mod out by whatever in both cases, that's the equivariant version. If I don't mod out by translating in the first case, or don't mod out by the global ideal generated by global linear functions, that's the FT equivariant versions.
There is a version for Bordism. Due to Jose Gonzalez and Kelly Carr.
I see. Yeah, I just didn't. So
Could you say those names again?
Gonzalez and Caro.
Gonzalez and Caro, yeah.
Right, what I'm trying to repeat the answer.
For equivariant algebraic Bordism.
Oh,
So the K-ring is not graded in any reasonable way.
K-ring, yeah, like there's no grading.
So far the description of a polytope as its indicator function does not play a role in the definition of the K-ring, right?
So here I don't mean just free abelian group generated on these indicator functions. I mean generally consider them as functions like so. So this is a subgroup in the space of all functions from Rn to R. So relations like, maybe I'll borrow this board. So things of this nature. It's baked in. Oh, thank you. Yeah, as written, this will be false. So as Alan mentioned, one would expect some sort of inclusion exclusion, especially on the K side, and it does hold. And it's baked in by saying we're working with indicator function. One can work with other notions of kind of, these are what's called valuative relations. One can try to work with subdivisions, which can cause some pain points. Here we're just working with indicator functions. And part of the appendix in my paper with Junie and Matt is to sort of clear out some of those discrepancies. So. Yeah, there you go.
In the case of the fan is not unimodular, what can you say about that equality of the?
Oh, that's a question in the appendix that I don't quite know how to answer. So even if it's complete, let's say I'm looking at complete unimodular fan, and at the very least right now, this, we don't know to what extent is true.
Okay, we know it's false. For example.
In general, it is false. In general, it is false. Yeah. In general, it is false. This equality will fall apart, but this description as piecewise polynomial over a global linear function, that will survive. Okay, so with this description of the two rings, let's get even more combinatorial by specializing to a situation where now we'll only consider the following projective unimodular fan, the so-called permutahedral fan. At least definition-wise, this is normal fan of the convex hull over all permutations of the, let's say, the integer vector 1 through n. You permute the coordinates, take convex hull, and take normal fan. So for instance, when n equals 3, this is a picture for the convex hull. For instance, it'll be 1, 2, 3, 2, 1, 3, and so forth. And normal fan looks like the one as expected that Federico drew yesterday. And here's a terminology. So we call a deformation of a permutahedral fan a generalized permutahedra. I'll abbreviate that as GP. And one fact that makes study of these generalized permutahedra quite rich is that many different combinatorial objects arise with generalized permutahedra, providing you some polytopal model. So inside this class of generalized permutahedra, in some precise sense, you can build a generalized permutahedra for every graph and study graphs through that way. Matroids. And posets and so forth. Oh, well, posets, there's a small footprint I should add that you do extended generalized permutahedra. But in any case, lots of combinatorial objects where sort of the primary thing going on in the background is either subsets or some permutation group arise as generalized permutahedra. And to list all the references studying things in this direction will be a little too much. But I hope I'll be forgiven by referring you to a wonderful paper by Marcelo Aguiar and Federico. I think it is published after all. Yeah. So the work, I mean, when this appeared on arXiv, it's like several years before this. And then when the work was actually done was like even much before this. You can take a look at some comments in the paper to see what kind of story is there. But anyways, here they study a half monoid structure on these polytopes. It also serves as a really wonderful survey into study of generalized permutahedra and their combinatorics. So I'll refer to that as one place you can look for survey. And there are many results that I like about generalized permutahedra. But let me highlight one for time's sake today. And this one due to Postnikov. To state it, I need one more notion, which I will define by just drawing some pictures. So if I take Minkowski sum of these three things, it looks like, well, turns out to be a permutahedra, although that's not critical. But this is also Minkowski sum of the triangle plus the upside down triangle. Or written in a different way, one may write identities of this one. So you can consider what one calls signed Minkowski sum. And here's a theorem that we can now state due to Postnikov. So I need one more notation for a subset, let's say S, from the indices 1 through n by triangle sub S. This is the standard simplex of S, the convex whole of the standard basis vector, where I is an S inside. So it's a bunch of standard simplex, one for each subset. Here's a statement. It comes in three parts. First one is that every generalized permutahedra, let's say P, is uniquely a Simonyi-Minkowski sum of these standard simplices. So we may write P, a generalized permutahedra, is always equal in a unique way to a signed Minkowski sum over these standard simplices. I'm calling the coefficients A of S. So for generalized permutahedra, I'll start just writing P of AS. Here's the second result, which is that the volume of a generalized permutahedra, given in terms of these coefficients, is equal to the following. It's a sum over sequences of n-1 subsets products of the polynomials of corresponding type. Where the sum is over sequences subsets such that the following what Grothendieck calls dragon marriage condition holds. Let me just draw it instead of writing out whole. So okay, so on one side here is n. So 1, 2, dot 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 n. On the other side, there are S1, S2, it's n minus 1. And the S's being subsets, we get some bipartite graph. Just keeping track of which element is in which subset. And what are we summing over? We're summing over sequences of subsets such that for any removal of some element on the right-hand side, there exists perfect matching. I mean, the story in the paper explained there is, well, this is called dragon marriage condition because, well, there are people on the left side, right side, and dragon takes away one person on the right side. No matter how dragon takes away, there's still a perfect match. Okay. So the volumes of these generalized permutahedra can be concretely understood in terms of these matching problems. And third, which is even more surprising, is that if I try to count the number of lattice points, the following identity holds as polynomials in AS. So let's take generalized permutahedra and Minkowski sum away a standard simplex. So it's the whole ground set simplex. And I'm counting the number of lattice points. And turns out this is equal to some transformation of the polynomial for the volume. Where what does this transformation do? Whenever I see something like x to the k, you replace it by x times x plus 1 plus dot 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 x plus k minus, so it's like kind of raising power. So there's this kind of funky transformation of the volume polynomial that counts the number of lattice points. Rather mysterious why that should be, especially geometrically. So, and let me make a little bit more. You might think, okay, so I stated like the volume formula and some lattice point counting formula. And well, there is a concrete relation that's classical between the K-ring and the Chow ring, stated as follows. So first, if I'm willing to work over Q coefficients, there's an isomorphism determined by sending the indicator function of P to the exponential in the corresponding support function. It might look like an infinite sum, but because of imposing this relation, it becomes a finite sum. And not only that, one can make this diagram commute by correcting with what's called a top class. So the statement is there is some element in the Chow ring side called a top class, such that if I start in something in the K-ring, I want to compute the Euler characteristic map. Well, I can apply the exponential map first, multiply with the top class, and then take degree. And this fact that you need to multiply with the top class to make this diagram commute, I mean, this is the classical Hirzebruch Riemann Roch theorem. But combinatorially, this is a bit of a nightmare to use. I mean, simply because if you want to actually compute with the taught classes, you end up writing something like x over a minus e to the minus x. And then Bernoulli numbers start showing up, and at least I find it somewhat painful most of the time. For instance, I do not know how to get this lattice point count result in terms of the volume. I mean, clearly there's some relation between K and A, given this theorem, but I do not know how to relate 2 and 3 using that classical Riemann, for instance. So there is a classical way that these rings are related, but at least for many combinatorial contexts, yeah, I haven't found many uses for that.
Yes,
Yeah.
you probably said it, but in order to apply that formula in part 3, I want to think of that as a polynomial in the A's, and then whenever I see exponents apply D.
That's right. So if you would like, yeah, so this really is a identity in the polynomials in AS. So this is possibly my lazy way of writing. You have a bunch of AS's, and then for the coefficient corresponding to the full ground set, you treat it as n minus 1. So P of this, the first coefficient in the polynomial, you use the variable -1, and then for the other ones, a sub s. And as polynomials, these two are equal. Okay.
Sorry, Chris, so this x is like, I should consider it like a variable's x or?
Yeah, so whenever I see a variable a s to whatever power, you replace it in that fashion. And if it's like a monomial consisting of them, then you do it for every individual one of them to this. It's quite weird on first sight. Yeah.
So just to further clarify, you're applying this psi transform to the volume polynomial of.
The entire of the volume polynomial in the AS.
Yes.
Without this subtraction one. So here's a promised theorem that relates K and A in the special context of looking at permutahedral fan. This is the first paper that's listed. But here's the statement. There exists an isomorphism, which we call zeta for not really any good reason. Between the two rings. And first thing one should note is that it's actually an isomorphism over integral coefficients. We don't even need to tensor by the rational. So there's an integral isomorphism. And left like this would be a typical example of a badly written math according to Serre, to say there is an isomorphism. There's a unique isomorphism with the property that the indicator function of a standard simplex goes to 1 over 1 minus the support function of that standard simplex. Which again, this just notationally means 1 plus h squared, blah, blah, blah. Looks like an infinite sum, but after enough high degrees, it gets killed. Moreover, this isomorphism has a property that if I wanted to compute I of something in the K-ring of my permutahedral fan, this is equal to degree of, well, I apply the psi map to the element and then multiply 1 over 1 minus the standard support function of the standard simplex of the whole ground set. Okay, so the big standard simplex. Now that guy I can understand. Top class looks nothing like sums of powers of standard simplex support functions. And let me remark some corollaries from this theorem. And if I have time, I'll remark a little bit about proof.
His zeta is a ring isomorphism. We said it's a ring.
It's a ring isomorphism. Thank you. It's a ring isomorphism over integer coefficients characterized by this property such that, and it has the property also that you have some sort of Hirzebruch Riemann Roch looking formula that relates the Euler characteristic to the degree. So one corollary is that it recovers the work of Grothendieck. I won't get into full details of how, but I mean, this really plays into for some things, thinking about Minkowski sum is easier. But for some other things, thinking about intersecting these in this Chow ring is easier with many tools that Federico mentioned yesterday. And with the interplay between those two and with this relation between the lattice point counting map and the degree map, which is the volume computing map, one can recover from that theorem with a little more extra work, this result of Grothendieck. So parts 2 and 3 can fall out from this theorem. I'll just make a remark, since I said I will not talk much about matroids in this talk, that it recovers many identities that concern numerical invariance of matroids. So for instance, Federico told you about, how many was there? Like 4 different ways of getting a formula for the characteristic polynomial of a matroid in this Chow theoretic, intersection theoretic way. This can add one more even. Okay. In fact, using this result and one more result in the paper BEST, one can actually recover many. For instance, there's a K-theoretic way of expressing the top polynomial due to like Spink and David Spire. And there's like many more, some of which that Federico mentioned. All of them, you can relate them using the Riemann-Roch theorem, this weird exceptional Riemann-Roch. Let me say a few words about the proof. So the original proof in the paper is through T equivariant. This. And here what one does is there is yet another way of describing both the K and the Chow ring in the setting of T equivariant, K-ring and Chow ring, in terms of you're looking at piecewise Laurent polynomials in some sense, and then there's the piecewise polynomials. And because this span has some very special properties, you can relate the two descriptions in a certain way. And using that description, one can build this kind of isomorphism. So in that sense, it's like, it kind of doesn't see any of the geometry. You're just playing around with two explicit descriptions of the equivariant versions of these rings and trying to relate them together. Yeah.
When you're getting to the meat of how you can do this, I think it's easier to me to compute H delta S. But then I don't see any way to turn that into a vector bundle. You have a piecewise polynomial. How do you turn it into a vector bundle situation?
So in the dictionary in toric geometry, the piecewise linear functions give you line bundles. And well, piecewise polynomials, one can think of that as products of the first term classes of those line bundles and so forth. But yeah, I'm sorry to say I will not go into how to build vector bundles from matroids and how that plays in. I just want to focus on this kind of weird isomorphisms between K and A. Yeah, Andrew?
Just to understand, well, maybe the geometric part of your bijection. So is it true that this bracket P, that's the K-theory class of some toric subvariety, closed subvariety given by the polytope P?
So yeah, the dictionary is this P. You should think of this as, well, a polytope defines for you some divisor on the toric variety, and it's that line bundle. It's a globally generated line bundle. So 1 minus P inverse would be the hypersurface given by that divisor, or structure sheaf of the hypersurface given by
You only get device. Okay,
Yeah.
okay, thanks.
But the key thing, that the P's are only about ample divisors, but that's enough to Z generate.
P's are about, yeah, base point free line bundles, and under the projectivity hypothesis, they're in.
So is it, so 1/1 minus h though, is that doesn't look like a piecewise polynomial function. It looks like there's something being inverted.
So this is, let's say, a shorthand for 1 plus h squared plus dot dot dot.
But that still doesn't look like a poly.
So that first, if it is 0 after some point, under the relation that we have modded out by global linear functions, the claim is that, okay, after some point it's gone, and then now I think it's believable that it's piecewise.
Because H is positive degree in your Artinian ring A.
That's one way, yeah. So yes. Okay, so there was one proof. There's actually a proof of this result in fact, a little more general setting due to Matt, Chia, Sam, and Nick Profit. I think it's 24. And I'll just say kind of loosely what one of the observation that goes behind this is. So the proof here is a little more geometric. And the observation is that this kind of isomorphism does arise for Pn. Because both are polynomial ring in one variable modulo power of that variable. So you're mapping the class of a structure sheaf of a hyperplane to the class of the hyperplane. And one can hope maybe this kind of picture can be used to prove, in fact, this, knowing that, for instance, the permutahedral variety has a rather distinguished embedding into products of projective spaces. So they have a much more geometric proof that at least I find a little more satisfying. And it actually generalizes to K-rings of matroids and Chow rings of matroids as well. But I will not go so much into that. Okay, now to finish up, if you were at FIPSAC, I think 2 years ago, there are all these stickers that you always ask. It's like a AN or a BN or whatever. It's like, what about type blank? It's a C. What I wanted was a B. So looking at post-college result, yeah, it's a natural question to ask, oh, what about type B or C or any other considered type? And that's been open for some time. So I'll tell you a story where we now resolve, at least in type B, what the right analog of this result of post-college. Let's see, what can I erase? Maybe I'll erase this. So yeah, maybe I'll replace this board with, well, now let's think our fan is the type Bn permutahedral fan. By definition, this is convex hole, all sign permutations of the vector 1, comma dot dot n. When n equals 2, the polytope looks something like this. So this would be 2, 1, 1, 2, minus 1, 2, and so forth. And you take the norm. So this would be B2. We have type B from the permutahedral fan. And indeed, one can talk about type B, generalized permutahedra. So this is the deformations of the type B permutahedral fan. And just like how a lot of the combinatorial objects with the symmetric group in the background arise as generalized permutahedra, the combinatorics of signed things appear as objects in type B generalized permutahedra. So let me make that a little more precise. We say that a subset in indices 1 through n and 1 bar through n bar is a signed subset. If for every k, not both n and k bar is an S. So for each element, at most one of the sign appears. You're thinking of bar as a negative. Let's see. So here's the theorem, which I think I'll kind of squeeze it in this one. So for a signed subset, let's now define a standard simplex with this little circle. So this is just notation for a convex hole of standard basis vector, one for each given by signed subset union the origin, with one notation to note. What I mean by E sub, say like 2 bar, E sub k bar just means minus E sub, just notationally. So I have a bunch of these simplices with now the origin included. And the statement is there exists a unique isomorphism from the K-ring of the type Bn permutahedral fan to the Chow ring. Once again, over integral coefficients, such that the class of these simplices go to 1 plus. So again, there's some kind of weird exceptional isomorphism that's really specific to this fan. And I'll use the board of last resort. Moreover, same sort of Hirzebruch Riemann Roch theorem. So let's name this P. So I apply P G times 1 plus H. 1 about 1 plus H. So there's a similar kind of replacement of the Todd class that, I don't know, at least I find it much more understandable. And here is the promised statement that generalizes Postnikov's result. So what's the first statement? Well, I'll be almost copying the three parts. One is erased, but these parts. So every type Bn generalized permutahedra is uniquely a Simon-Minkowski sum of those kind of rotate around standard simplices. So these are non-empty sign subsets. And two, the volume also has a nice interpretation. So if I write my type B generalized permutahedra in terms of those coefficients, what's the volume? And once again, it's a sum over some sequence of sign subsets, n of them this time. And here we need a notion of signed transversals of the sequence times the corresponding monomial. Now, what's a signed transversal? Let me draw it. It's some sort of a matching problem, once again. Now, on the right-hand side, instead of just 1 through n, I have 1 bar, 2 bar, n bar. Then I have sign subset S1, Sn. Okay. Now, no dragons this time. I'm sorry. But what is a sign transversal? It is a size n signed subset. So it's a maximal signed subset having fixed n. So let's say 1 or 2 bar and so forth n, such that we have these sign subsets. So I have this bipartite graph again. There's a perfect match. So I count the number of signed transversals, or these maximal sign subsets, such that there is some matching. And that's the coefficient that goes in front of this. And I'll finish up by saying there's a similar relation between the volume and the last point count. I'll abuse notation in a similar way, where now instead of taking away the standard simplex, I take away the unit cube and try to count the number of lattice points. And this is equal to, once again, some transformation of the corresponding volume polynomial. And this transformation is a little more ugly. It transforms x1 d1 dot 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 xn dm into the inverse of the multinomial coefficient times x1 binomial polynomial d1 . So there's a exact analog of Postnikov's result in type B that really mirrors each other. The volume is counted by some sort of a matching problem, and the number of lattice points is counted well by looking at some corresponding volume point. Okay. And once again, the technology that goes behind this is this weird and exceptional isomorphism, very particular to the type Bn fan. This time I skipped much of what goes into the story of matroids, but I think there's a lot more to understand about these weird exceptional isomorphisms between K and H or K and A. And if you were at UA's talk last semester, there's a story about multi-matroids where, well, why stick with signed permutations? Why not go with weak product of Sn with some cyclic group? And one can ask similar questions and see if there is another exceptional isomorphism there. I think so, but unknown and so forth. And with that, let me conclude here.
Do you expect such an exceptional isomorphism to be there for all Coxeter matroids, using like similar techniques, or are the techniques very different from type A?
Yeah, so every proof, so in type B, there is no like even like a geometric proof. In type A, I mentioned there's a rather, at least explanation that I find satisfying. For type B, it's really like getting down and dirty with the kind of combinatorial description of these rings, very specific to Bn. We have no idea whether it will even generalize to type C, D, or anything. So it's quite specific in each type. It's quite funky and weird. Yeah, Alan?
What about affine type A?
Probably, actually. Yeah, but I've certainly not thought it.
Let's talk about it. So the permutahedral variety is generated by Chern classes on some line bundles. That's clear because it's a toric variety. Sorry, I'm saying the Chow ring of such a thing.
Yes.
Are the relations generated by universal things like the Whitney relations that Sam mentioned for the Grassmannian yesterday? I mean, there are many descriptions of relations, but there's a
I'm not sure. There are many presentations of the Chow ring, for instance, with those standard simplices giving you the generating variables. And for that one, there are some very nice presentations. Is that the one that you might be thinking of? I'm not sure. So I can show you a few things. Okay. And let me take someone back.
What happens when you compose like the isomorphism you give between K of sigma and A of sigma, like with the classical one?
Oh,
And then you get,
I don't know. Yeah. Don't know. I mean, certainly as soon as I use the classical one, I'll have to exit integral coefficients. But do I get something used? But I'm not sure. Yeah.
So every type A permutahedron, generalized permutahedron, is also type B generalized permutahedron, right? Or at least there's a way
Yes,
to-
yeah, there is a way to make.
But these results look a little bit different than the type, like not generalizing the type A ones. What happens if you restrict to type A in these type B results?
So there is a slight kind of cheat that I did. For instance, when I said like volume here, I mean, you might notice that all these simplices live in a hyperplane where the coordinate sum equals a common number, right? So really, I'm talking about volume inside that hyperplane. Whereas in type Bn, it's really just volume in Rn, as is. So first, there might be some discrepancy that I don't quite see how to resolve immediately. But maybe one can, maybe there's some tricks to get around.
And the isomorphism, if you restrict it to the subring of type A generalized permutahedra, does not remain an isomorphism?
Yeah. So if I kind of coarsen the Bn to a version of type An minus 1 fan inside Bn fan, I don't think the two things agree. Unfortunately.
Okay, Anders maybe is.
Okay.
So you say you don't know how to do type C. I thought type B and type C was the same setup. Do you have any lengths of roots showing up anywhere?
So yes, the root length is different. One has two en versus or two like times the standard, whereas Bn is one, and that actually plays a role. Yeah. So for us, like we actually care the lattice structure, the root lattice structure. Like we really care about that lattice structure. So we don't quite know how E1 applies.
But I don't see anywhere in your picture that
It changes which polytopes are lattice polytopes.
That's true. For instance.
Martha?
Oh, yeah, I have thought about these kinds of Toric varieties when I think about Hessenberg varieties. And I know there's an action of the vowel group on a cohomology. So in your nice description of these rings, like your type B vowel group is going to act naturally on the Chow ring of your Toric variety here. Is there a nice description using your language of what that action looks like? Like Stembridge has a paper that computes what the representation is, but I don't know of any nice concrete combinatorial rule for computing this.
I don't think our result does so. Yeah, at least I haven't pursued it. And if anything, we use the group structure to simplify some of the groups.
Is this theorem on the archive?
Oh, yes, all these are actually published.
Okay.
Okay, so
Sarah.
So in light of the math overflow question, the first one last night, are there examples of things that you're computing, you can compute now in this, with this technology that you wouldn't have been able to compute if you're just looking at ordinary cohomology description for Toric varieties or the K theory?
Let's see. Sort of, yes, but I mean, one could always argue like where the boundary exactly is. A lot of the matroid invariant thing that we compute, one could argue that you start on the K side and do a combinatorial first, and then go over to Chow side. Or one can say it feels easier, but not quite maybe a banger that we're looking for to counter whatever happened yesterday. So at least I can't quite think of one at the moment. Yeah.
Maybe the Postnikov in type B, EN.
Sorry?
Maybe Postnikov's results in type B, and those use your technology. They're the analogs of Postnikov's results in the type B setting. Your technology, maybe.
Yeah. So I guess, yeah, that's one.
okay, so let's